So today we will start with the bit field processing and manipulation instruction. These instructions are important for your examination as well. So please make note of this instruction, the operation and working of the instructions under bit field processing and manipulation instruction. So let us start with the first instruction. First instruction is CLZ, that is count leading zeros. CLZ stands for count leading zero. CLZ.W space RD comma RN. So source register is RN register, destination register is RD register. Dot W indicates this instruction syntax supports for 32-bit thumb 2 instruction set. So next, now let us see what's the operation of this instruction CLZ with an example. So we have an example here, CLZ space R1 comma R0. R0 content can be anything. So here you have R0 content as shown here. Now you have the data 00, as this is a 32-bit register, you have some data. So what does the CLZ instruction do? It will count the leading zeros. So it will count the leading zeros starting from the most significant bit of R0 register. So here R0 register most significant bit starts here. It starts counting the leading zeros from the most significant bit till it finds the next logic 1 bit. As this is represented in binary, it starts counting the leading zeros in R0 content from MSB till it finds the logic 1. So here from MSB till here, let us count how many zeros are there. So we have totally 27 zeros. So this 27 will be present in R1 content after execution of this instruction. So what will be the content of R1 after execution? It will have the total number of leading zeros present in R0 register starting from MSB till it finds logic 1. So next instruction is rbit.w space rd comma rn. So rbit stands for reversing a bit data in a register. So reverses the bits. So we have an example, rbit space r1 comma r0. R0 is a source register. So R0 content, we have some data here as shown here. So what does rbit do? It just reverses the data and stores it in the destination register. So the destination register here is R1 register. Whatever the least significant bit you have in R1 will move to R0 will move to R1 register, and the most significant bit in R0 will go to the least significant bit. So it just reverses the position, every bit position in source register to the destination register. So hence you can see the contents of R1 register after reversing the data. So this is rbit instruction. Next we will see the next set of instructions. The first instruction under next division is BFC. BFC is clear bit field within a register. BFC stands for clear bit field within a register. Now let us see the syntax. Syntax is bfc.w space rd space rn space rd comma rn comma ash lsb comma ash width. So this is the syntax for the instruction. Now let us analyze the operation of clear bit field instruction using an example. So I have instruction here as shown. You can just see the instruction here, bfc.w r1 comma r0 comma ash 4 comma ash 8. So now I'm loading the register with some constant value. Whenever you are using LDR and you are trying to load some constant value into the register, you have to use equal symbol. Okay, so it is not ash, it is equal. Suppose if you are using move instruction, then you can have ash as a immediate data. But as you are using LDR instruction here, you for loading the constant value into the register, you have to use a symbol equal. Now you have loaded the R0 content with some constant value. Let us say the constant value here is 1234 FFFF is the data. Now immediately after this instruction, I have used bfc.w r1 comma r0 comma #4 comma #8. Now let us see what happens in this instruction. So we have represented the content of r0 in binary. That is 1 2 3 4 ff is represented in a binary. Now if you just look into the instruction, it just gives the position. #4 gives the position of the bits in a source register. So #4, that is #LSB field, we have the data as #4. It represents the bit position. Now let us see fourth bit position. Where is fourth bit position in R0? The fourth bit position starts from here. So from fourth bit position, how many bits I need to consider? That will be given in #width field. That is #8. That means 8 bits I have to consider from the fourth bit position. So from fourth bit position, I will consider the next 8 bits. Okay, so 1 2 3 4 5 6 7 8. These 8 bits I'll consider. What is your actual instruction? Bit field clear. Whatever the field you're selecting, the bit field you're selecting, that will be cleared in the source register, and the same thing will be copied into the destination register. So which is the selected field, it is from fourth position and till 8 bits from the fourth position. You have selected this bit field. Now this bit field will be cleared and the data will be loaded into the destination register R1. So finally, after execution, what will be the content of R1? The remaining data will be the same, but the selected bit field from fourth position to till 8 positions, 8 bits from fourth position will be cleared. So this will be the data after execution of PFC instruction as shown from this example. I hope everyone have understood what is bit field clear. Okay, next we'll move on to the next instruction, BFI. That is insert bit field to a register. So we have the syntax as bfi.w rd, rn, #lsb, #width. Now I have the instruction as shown in the example here. So before we go to the example, I am storing the source register. I'm using two registers, Rn and Rd as R0 and R1. Source register and destination register as R0 and R1 here. So I'm loading some constant value into these two registers using the instruction LDR R0, equal to 0x12345678 for R0, and next instruction LDR R1 comma equal to 0x3355 AACC. This 32-bit data I'm loading it into R1. I'm repeating, if you are using equal to, it means that you are loading some constant value into the registers here. So after these two, after loading the data, initial data to R0 and R1, I'm using instruction bfi.w r1 comma r0 comma #8 comma #60. Now what is the instruction you're using? You're using the instruction bfi. That means insert bit field from source register to the destination register. The bit field position and number of bits will be given in the instruction itself. Now the #16, the data #16 indicates the total number of bits you need to select in the bit field. Okay, so this indicates the total number of bits, and the data #8 indicates it indicates that in the destination register from which bit position you need to copy the data. So this is reference with respect to the source register. This is with respect to the destination register, because you are inserting from source to the destination. Okay, so now let us analyze the same thing in the example. So R0 I have considered as 1 2 3 4 5 6 7 8. Same thing is represented in binary here, and R1 is also represented in binary. So now how many bit positions you have to select? Now it is given in width field, that is 16. So starting with least significant bit, it will select from 0th bit position to 15th bit position. always BFI starts with the least significant bit. You remember this, it cannot start with in between. It has to start at least significant bit. So how many digits how many bits it has to consider? 16 bits. So starting from 0, it will count 16 bits. So that is from 0 to 15 of R0 register. So this is the selected field. So this selected field will be inserted into the destination register. But where, from which position it has to be inserted? It is given in this data, this field, that is from bit 8. You can see from bit 8 is starting here from R1. So this data will be replaced in this bit position starting with 8-bit position. So you can see here. So what you have to insert? You have to insert 0th bit to 15th bit of R0 to 8th bit to 23rd bit of R1. Total it is 16 bits. Okay. So you can see after execution of the instruction, R1 content. This shows the R1 content before execution. Okay. This shows the R1 content after execution. You can see. Now, whatever is highlighted here is the replaced value from R0 register. Okay. You can understand, right? From 0th position till 15th. 5 till 15 because it's specified as 16. So 16 bits will be copied and it will be inserted from the 8th bit position of R1, and this will be the execution after BFI instruction is executed. So now let us see R1 data after execution. This I have represented binary and this represented in hexadecimal. Now what was before content of R1, before execution content of R1? It was 3355 AACC. So how many bits of data you are selecting? 16 bits because it's specified in the instruction. So from least significant, 16 bits will be selected, and where it is inserted? From the 8th bit. So from 8th bit means it starts from here, right? So it is being inserted. 5, 6, 7, 8 will be inserted from the 8-bit position. Finally, R1 content is 335678CC. So this is the operation of BFI instruction, that is insert bit field to a register. Next instruction is sbfx.w space rd comma rn comma hash lsb comma hash width. So it copies the bit field from source and extends the side. Now let us analyze the operation of this instruction. Now we have two registers, source register and destination register. I have used source as R0 and destination as R1 here. Now before I start analyzing the operation, I have to initially load some value into R0 register. I have to assume some value in R0 register. Therefore, I am loading the content of R0 with 5, 6, 7, 8 ABCD data, that is 32-bit data. Now, the same syntax is represented here as sbfx.w r1, r0, hash4, hash8. Now, in under hash lsb field, what you have? You have 4. Under hash width field, what you have? You have 8. Now, you have to select the bit field. You have to select the bit field. Now, let us see what is that bit field. Hash 4 indicates from which bit position. Okay, hash 8 indicates from 4th position how many bits you are selecting the bit field. Okay, so now 4 indicates the position. Let us now count 0, 1, 2, 3. 3 is over. Which is the 4th position? From 4th position is this, from this position. How many bits you have to consider from 4th position? It is given here. It is 8. 1, 2, 3, 4, 5, 6, 7, 8. So totally 8 bits you have considered in a field. Now this selected bit field from source register will be copied into the destination register starting from ls bit, right? This is the destination register R1. So whatever you have selected here, that will be copied into the least significant from least significant bit position. The same thing is copied here. Now, what is the most significant bit of this data selected bit field? It is 1. So you are extending the same data in the remaining bits of destination register R1. So assume that before execution R1 was 0, 0, 0, 0. After execution, what you are copying? You are copying BC because 4th position starts from here. and 8 bits. So what will be the selected data? It will be BC. BC will be copied from source register and it is copied to destination register from LS bit, and it is copied here. What is the most significant bit? It is 1. So that will be extended in the remaining bits of the destination register. So this is about the copy bit field from source and extend sign, that is SBF. Okay. Next instruction is ubfx.w space rd comma rn comma ash lsb ash width. So it will copy bit field from source register. There is no sign extension. It just copies the selected bit field from source register to the destination register. Now you have the syntax given here, and with respect to the syntax, we have an example: ubfx.w space r1 comma r0 comma ash 4 comma ash 8. So R0 is source register. I am loading the constant value into R0 register as 5678 ABCD. Now this ash 4 indicates the bit position. Ash 8 indicates the width. Okay. So now let us see. R0 is represented in binary 5678 ABCD. Where is fourth position? Fourth position is here. So from fourth position, how many bits you need to select? 8 bits you are selecting. So this 8 bits will be copied to the least significant bits of R1 register. And now this instruction indicates there is no sign extension. So whatever might be the most significant bit of the selected bit field, it does not bother. It will include the zeros here. Okay, there is no sign extension. So after execution of the instruction, R1 content will be 0x 000000 BC. So this will be the data. Next set of instruction is again for sign extension instruction. Let us now see. Here we are selecting bit field. Okay, you are giving the position and the total number of bits you are selecting. But this set of instruction, you are not creating any bit field here. Okay, this is just a sign extension instruction. So under sign extension instruction, we have again two types. One for the sign extension, another for not extending the sign. And with respect to both the instructions are with respect to byte as well as with respect to half word. Now let us see the first instruction, sxtb rd comma rn. The next instruction is sxth rd comma rn. Now, as I have considered the source registers and destination register for all the instruction here as R0 and R1 respectively, I'll assume R0 content as 55AA8765. It can be any data. We are considering 55AA8765. Now, first instruction is SXTB, that is sign extension. SXT stands for sign extension, B stands for byte with respect to byte. Now, as you are considering with respect to byte of the source register, what is byte? The least significant byte of source register. It will start with the least significant byte only. It does not consider any byte in between. Okay. So the least significant byte here is 65. How will you represent 65? 0, 1, 1, 0, 0, 1, 0, 1. So what is the most significant bit of 6? It is 0. So that 0 will be extended in the remaining bits of destination register R1. Okay. So next instruction is SXTH. So the next is sign extension half of half word. R1 comma R0 are the operand fields. Now half word is referring from the source register R0. What is half word? It is 8765, the least significant half word, 8765. So how will you represent 8 here? 1000. So most significant bit of 8 will be 1. 1 will, as it is 1, that bit will be extended in the remaining bits of the register R1. So as it is 1, it becomes FFFF8765. Yeah, that means you are extending the sign of the half word. Okay. So the next instruction is UXTB. That means there is no sign extension here. But what data you're considering, or considering the byte data of source register. So what's the byte data of source register? It is 65. So 65 will be copied into R1 register. You can see the least significant byte is also 65 here. Are you extending the sign? There is no extension of sign here. Therefore, it will be included. All the remaining bits will be included with zeros. Okay. So R1 content will be 00000065. Next instruction is UXTH R1 comma R0. So there is no sign extension again, but you are referring to what? You are referring to half word of R0 register. What is the half word of R0 register? It is 8765. So 8765 will be copied into the destination register R1. There is no sign extension, therefore the remaining bits will be included with zeros. So therefore, after execution of this instruction, R1 will be 0x00008765. So these are the 4 instructions under sign extension group. Next is call and unconditional branching instruction. We have seen and we have studied many call and unconditional branch instruction. Now let us see the mnemonics used under ARM Cortex M3. What are the call and the unconditional branch instruction? We have certain conditional branch instructions as well. Let us see that later on. So the first instruction under unconditional branch is B label. B stands for branch label. So there is no condition checking here. As soon as the processor executes this instruction, it just branches to the label and it continues the execution from the labeled address. Okay, branch label. There is no condition. Uh, Next instruction is BX register. So BX represents branch to address specified by the register. So instead of specifying the address directly in the instruction, instead of directly specifying, it will be specified in a register. So whenever you are storing the branching address in a register, you have to use a mnemonic as BX. So branch to a address specified by the register. Again, there is no condition here. Hence, it is a conditional branching. Next instruction is BL label. Again, there is a direct labeled address here. That is, branching address is directly specified in the instruction itself. BL stands for branch with link. So I told you about the link register. So whenever you have call instructions or branching instructions, it will store the return address. So whenever you specify the instruction BL, it will branch to the specified address, as well as it will store the return address where it has to come back in the link register automatically. So branch to label address and save return address in the link register. So the mnemonic used here is BL. Okay, next instruction is BLX register. Whenever you have X in the branching, that is unconditional branch instruction, it specifies that the branching address is not specified directly in the instruction. Instead, it is specified in the register. So here the address will be specified in the register. The mnemonic here used here is BLX. That means it will branch to the address specified in the register, and also it saves the return address in the link register. Okay, so these are about the unconditional branching instruction. Now let us see what happens when you have a branching instruction within different functions, that is a subroutine. So how the operation is performed. Now let us analyze. The main program starts here and a set of instructions will be executed, and the processor finds an instruction BL. So what is this instruction? Branch with link. Okay, branch with link register means it it branches to the labeled address, and also it saves the return address in the link register. So this happens before. Okay, now let us see BL function A. Where is function A? It goes here. The branching takes place to function A. What's the first operation? It has to first save the link register, right? So it pushes the, after it saves the return address into the link register, it also pushes the content of link register to the stack. for temporary storage. Later it executes whatever the instruction is present in function A. And within a function, again you have a branching instruction. So that is BL function B. Now the instruction used here is BL, branching along with saving the return address in a link register. So now branching takes place. Where it goes to function B. Automatically the link register saves the return address. Okay. So return address means the next instruction address. So again, when it before it starts executing the instructions in function B, first operation is it pushes the link register content onto the stack. Later it continues with the instructions present in function B. Okay, now at the end of the execution of function B, you have an instruction pop PC, where what is the function of PC? PC holds the address of the next instruction to be executed. So it has pop a PC. Now this instruction automatically retrieves back the return address from the stack. So which was the last return address which is stored? It was from function A, right? So this address will be popped and the control will come back here. It starts executing, continues executing. Again, it has an instruction pop PC. So what will be the last, the previous link register, the return address which is stored, so that will be popped into PC and the control will come back to this position, that is main program. So then it continues execution of the program. So you can have the different functions, a function within a function, and you can also have a branch instructions which can be used in different functions. Okay, so this is how we can understand the importance of link register, automatically storing the return address using link register, and that included in a branch instructions.